ahead and record this. As you will see for a lot of chapter 11 here, and it started last time, is that it's quite difficult, right, to say what a series converges to. So in 11.2, we got a little bit spoiled, right? Because we could say not only if the geometric series converged or diverged, but when it converged, we could say what it converges to. And that was very nice, but unfortunately short-lived. In 11.3, you can see that we've just have fallen on, well, can you say if it's basically a finite number or not? Does it converge or does it diverge? And so I have this little spiel here at the beginning of today's class saying that, yeah, I understand that this is a bit disheartening, right? And it is abstract and whatnot. But I'd like to show you what it takes to show that a relatively simple series converges to, and we'll show here that summing up from n equals 1 to infinity of 1 over n squared. We've seen with the p-series test that this converges. Maybe it's the simplest case besides the geometric series of something that converges. And it turns out this took mathematicians, as it says here, over 80 years to solve. They knew that it went to about 1.645, right? They expanded out from many, many places, and they knew approximately what it was, but they couldn't figure out exactly what it was. And it turns out that this ends up being pi squared over 6, which is kind of remarkable. How does pi get in there? And in fact, there's a very nice video done by the 3 Blue 1 Brown on a different proof for this, also a very clever proof. But I'm going to show you kind of the original proof. This is called the Basel problem, by the way, named after the town of Basel in Switzerland. Switzerland, I believe, yeah. So yeah, it relies on something fairly complicated here, that you can rewrite sine as an infinite polynomial. And this is the way that you would rewrite sine as an infinite polynomial. We will get to that here in chapter 11, and that's kind of where a lot of chapter 11 is going, is that we're not going to just write out series that describes particular numbers, like this one right here turns out to describe pi squared over 6, but we're going to be able to write out series that describe functions. These are going to be called power series. We'll also have a section about Taylor polynomials and all this sort of stuff. And so this right here, this infinite polynomial, this series, when you add up lots and lots of things, turns out to be exactly sine of x, or it converges towards sine of x. And so, okay, I'd like to give you the idea of the proof here. Let's see if I can't switch over successfully. All right, so here is the Basel problem. First, a little bit of history. This was first posed in the 1600s. I really don't know this mathematician or what they're particularly famous for, but this was Euler's kind of claim to fame, who is arguably the best mathematician who has ever lived, both in the quality and the quantity of his work, just all around outstanding. I'd be happy to do another math is interesting talk specifically about Euler, but you can see here that over 80, close to 90 years, in fact, went by. So yeah, it kind of at the time, some leading mathematicians, the Bernoulli family. There's a lot of Bernoullis, by the way. There's always like a Jakob and what, they're all like J names and stuff like this. They're in Switzerland, but anyway, there's a whole bunch of Bernoullis, and patriarch of the family, right, tried to solve it for a long time, gave it to sons and cousins and all this sort of stuff, said, hey, try to find this. And Euler, turns out, who was studying with them, kind of realized quite early on that he was a very gifted mathematician, was able to solve this. And so yeah, this problem is named after the hometown of Euler. And so, okay, here's the formal statement of the problem. I feel like I've already described this, so I'm not going to go into a lot of detail. But again, we're trying to figure out what is the sum of the reciprocal of the squares, right? So this is 1 plus a 4th plus a 9th plus a 16th going so on and so forth. And like I said, it goes pretty close to, 1.645, but they wanted to know the exact value. And again, all of this is premised with that this is difficult, right? It took mathematicians over 80 years to figure this out. This takes a couple of brilliant ideas, and this is why that we do not ask you in our class to say what exactly something converges to. Because again, it took the leading mathematicians of the day over 80 years to solve this problem, right? And so it's not really realistic for us to ask you what something converges to on a quiz or an exam that you get, 20 minutes or 60 minutes to solve. And so, okay, there's a couple of brilliant ideas that you need. One of them is this weird factor theorem. And so I'd like to describe it for just a polynomial first. So if you have a polynomial with certain zeros, right? We're always interested in finding the zeros of a polynomial, right? Factoring this thing and setting it equal to 0. But if you have some polynomial and we can write down what the zeros are, and better yet, we can say what the constant term is, then if one was so inclined, you could factor it like this. And you could say this is a completely useless theorem, right? Why would anyone ever want to factor it like this? But the big thing is, if you wanted to, you could, and we'll see a use for it coming up like right now. But you can see, for instance, right, if you go ahead and you plug in everywhere that you see an x, if you plug in your first zero, z1, for instance, look at that first term or that first factor, you get 1 minus, and you plug in a z1, it's being divided by z1. So you'd get z1 divided by z1, that's 1. So 1 minus 1 is 0, and then you can kind of forget about the rest of the stuff. All right, so let's just take it for granted that if you wanted to, you could factor things like this, even though it's weird. And so maybe I'll give a quick example. If you wanted to, you could factor x squared minus 5x plus 6 in this way. We know that the zeros of this, if we did like our normal factoring, would be 2 and 3. So we could factor it like this. You can see where the 2 and the 3 live. But the only thing I'm missing is that the constant term is 6. If you were to actually FOIL this all out, you'll see that I'm off by a factor of 6. And so that C term, that 6, needs to go out in front there. Okay, fine. What does that have to do with what we're interested in? And that is, this kind of sine function, and in particular, this Basel problem. So what Euler realized is that if you applied this weird factor theorem to not just a regular old polynomial, but an infinite polynomial, that it behaves just as well, right? So here's a sine of x. And in particular, you can see that all of these terms have an x in them. So maybe you want to go ahead and factor that out, and we can put these on the other side. Now, all of the factors for sine of x over x come in pairs, right? All of the zeros, I should say, all of the zeros. And what we're going to end up looking at here turns out to be very important, but it's not at all, obvious at this point here, that this coefficient in front of the x squared, this negative 1/6, ends up being very important. So you'll see this at the end when we point to it. But okay, so we can go ahead, and the first brilliant idea is that the sine function has something to do with the answer, right? Again, kind of remarkable. And if you write it in its infinite polynomial form, okay, good things happen. And so the second brilliant idea is, like I said, use that weird factor theorem to go ahead and factor sine. And of course, when you factor it, because there are infinitely many zeros, infinitely many places where it crosses the x-axis, of course, you're going to still have an infinite polynomial. So you can see, right, the zeros for sine are, well, at 0 itself, at pi and negative pi, at 2 pi and negative 2 pi, at 3 pi and negative 3 pi, right? They always seem to come in pairs, right? There's a positive one and a negative one, but it happens at multiples of pi. So, okay, we'll go ahead and we'll factor sine like this, right? Using this weird factorization theorem here. Next thing. And again, just like the last time, we're going to go ahead and divide through by x. And then we're going to go ahead, and the last thing here is that we're going to combine these pairs. So, right, the pi and the negative pi, the 2 pi and the negative 2 pi, right? All of these are nice products of conjugate binomials. And so when you expand them out, when you FOIL these pairs out, right, you get a difference of squares. And in particular here, you can start to see, look at those denominators. We have 1 with the pi squared, and then we have a 4 with the pi squared, and then we have 9 with the pi squared, right? We get perfect squares, 1, 4, 9. And so you can see the very, slightest glimmer of hope here that we're actually leading towards something, towards a solution here. Again, remember, over 80 years for anyone to look in this direction, because it's so weird, right? All right. So if we take this, the infinite polynomial in this weird factorization theorem way, and we look at all of the pieces that have an x squared, all of the ways that you could combine and you could get x squared. Well, I guess maybe even before that, let's think of all the ways that you could just get a constant, right? If you want to get a constant out, you need to be multiplying, right, infinitely many ones together, essentially. So long, if you choose any other combination of these things, because remember, you're going to have this huge foiling out, this huge expansion. And remember, in order to get the full answer, you'll need to multiply every single one by every single other one, sort of deal. And but the only way to get a constant is for all of the ones to be multiplied together. If you have anything with a variable, right, there's no way to cancel an x squared later. So long as you choose one of the x squareds, you can't ever go back. So here's where we can think of all of the terms that give you, an x squared term. Well, if you choose in your first factor here, you choose the negative x squared over pi squared, and then the rest of them are constants, right? Because you can't have any more, because then you'd get up to x to the fourth. But if you just choose one of them and you choose it in the first one, that would give you an x squared term. So let's go ahead. We're going to collect all of the x squared bits. So I'm just going to factor it out. Another way that you could get an x squared bit is something like this, right? If you choose one for the first one here, and then in the second one, you choose the x squared over this 4 pi squared, and then the rest of them need to be ones, because again, if you choose more than one x squared bit, you're going to have x to the fourth or x to the sixth, right? When you multiply together x squareds, that keeps on, growing in degree. So notice here you would have this negative 1 over 4 pi squared. Again, I'm going to factor out the x squared. And we can continue this. Here we go. And it keeps on going. And so if you factor these things out, in particular the negative 1 over pi squared as well, you get exactly the series that we're interested in finding the exact sum for. So we go ahead and we take this and we compare it with the normal polynomial expansion for sine of x. In this case, we've divided through by x. And we can see that when you sum to all of this here, you should get negative x squared over 6. And the only way that these things would be the exact same function, right, is if those coefficients end up being the exact same. And so we go ahead and we set those equal to each other. We can cancel some stuff out, the x squareds, we can cancel out the negatives, all that sort of stuff. And the last step is to bring that pi squared over. And here we have the infinite sum of the reciprocals of the squares, right, equals pi squared over 6. And thank goodness, when you plug in pi squared over 6 into your calculator, it is indeed very close to 1.645 and change. So this right here is the answer. Again, took mathematicians a very long time to find this. This is the proof of it. This is kind of the original idea that Euler had in order to solve this. And yeah, that's why, unfortunately, we cannot feasibly ask in our class, right, what a series converges to, unless if it's a very specific series, like a geometric series. We will get a little bit more powers later on when we bring up Taylor polynomials and things like this, and we'll be able to say what a few more things converge to, but in general, these are very difficult problems to say what they exactly go to. Whew. All right. The end. All right, so I know that this took some time, and I knew it was going to, because again, complicated thing. But yeah, so that's why we don't ask what something converges to in general. We just ask, does it converge or does it diverge? Yes, and then they lived happily ever after. All math was done. All right, well, with that, today we're talking about the comparison theorem. Oh, and I've misplaced, there we go, my video notes. So in the comparison theorem, I need to get down to my notes that we did in the video. We have two different types of comparison theorem that we're going to be talking about. We're going to be doing a direct comparison theorem which the proof for is relatively straightforward. We've even already kind of talked about this. And this is the same comparison theorem that you did for improper integrals in chapter 7. So again, it just basically says that if you have a smaller thing diverging, that a bigger thing must also diverge. And if you have a bigger thing converging, well, then a smaller thing must also converge, so long as everything is nice and positive, right? So again, kind of we have this restriction here that we need to have all positive terms, which luckily so far we've mostly dealt with this. This is a great stepping stone, and you need this to prove the limit comparison test here. But I would say that when it comes to problems that you're likely to see in our homework and our quizzes and our exams, things like this, the limit comparison test can solve about 90% of them quite easily, maybe even 95%. So the limit comparison test, I would say, is in general a stronger test, that it can solve more things, that it's easier to use. And so I would recommend, and we'll see some of the notes today is kind of emphasizing why the limit comparison test is stronger, why I'm claiming this. But still, there are that 5 or 10% of problems out there that the limit comparison test cannot solve, that you do have to rely on the direct comparison test for. So this is not to say that you can just forget about the direct comparison test. The limit comparison test does it all. That's not true. You need the direct comparison test as well. All right. From that, we do a lot of problems. We do both with the direct comparison test method and with the limit comparison test method, all that sort of stuff. And that's what today's lesson is going to be about. So I thought I saw some hands up. Let's go ahead and call on a few folks for questions, and then we'll get into our problems for today. Jeff, you have the floor.
Thank you, Professor. I just wanted to make sure that I understood this right. When I'm using the limit comparison theorem, our test, I'm now in the realm of sequences while I'm using that instead of series.
So this is very similar to like the test with, the integral test. We are coming up with a system to tie together things' fates, right? When we were talking about the integral test, if we showed that these hypotheses were met, then we found that our series shared the same fate as our improper integral. That is, if one converges, the other converges. And if one diverges, the other diverges. With the limit comparison test, this is very similar, but our hypotheses are different. The hypotheses here are very, actually, they're relatively simple, right? You need positive terms, right? And you need that they are relatively the same strength. And when I say relatively the same strength, that if you take the ratio of them and you consider as n goes to infinity, that they're only off by a constant, right? So this is going to be equal to c. So this is, remember last time I think you asked about, and we talked a little bit about if you did like 2x squared versus x squared. And I said, these aren't really maybe different enough sort of deal. Right. And if you were to take the ratio of these, right, you would see that according to the limit comparison test, like these are only off by a factor of 2, right? They are kind of the same strength. And so this ties the fates together, hopefully with a, one of these will be relatively complicated. One of these should be relatively simple. And once we've tied their fates together, we know that if one converges, so does the other. And if one diverges, so does the other. So yes, you do temporarily use just the items on the lists to tie their fates together.
The reason I was asking is because like at one point you had 1 over n, and that converges towards 0 in a sequence, but I believe it diverges in a series.
Yes.
So I needed to think of it in a sequence, not a series.
We're just going to be applying this here, essentially, for the test to tie these things together. And then everything else is done in terms of the series.
Okay.
So you're only talking about sequences for just the smallest blip, right, when you're doing this comparison to tie their fates together.
Right. Thank you.
Yeah. Let's take one more question from a raised hand. We'll check on the Q&A and then go from there. I think, Zaid, I believe you had your hand up next. You have the floor. If you have a question for us.
Hi, can you hear me?
Yeah, sure can.
So I had a quick question for the pre-class notes on the last example. It's like a small question.
Okay. Oops.
So the last step where you have like -1/2 e to the negative x squared from 1 to t, right? On the right.
On the right over here.
Yeah.
Okay, yes, I'm with you.
When you plugged in 1, why is it to the -1 and not just +1?
So it looks, this is my function here that I'm plugging things into, right?
Mm-hmm.
So, and I'm plugging in 1 in for x. So there's still a negative out there, right? So this needs to be
Okay.
negative times 1 squared. So when I take 1 and I square it, you get 1, and then you apply a negative to this. So it is very important. And this is actually, it comes up quite a lot that with all of these, when you're combining together exponentials and multiplication and whatnot, you really have to revisit, this PEMDAS thing, right? The order in which things happen, because sometimes students will type into web work or whatnot, like -1 to the n. In comparison, right? Something like -1 raised to the nth power like this, right? These are two wildly different functions. One
Mm-hmm.
is alternating back and forth, and one is just exclusively -1.
Okay.
So,
Perfect.
right. Yeah. So exponentials first, and then you do your multiplication.
All right.
All right. Anything in the Q&A that we should talk about before we try another problem here?
Is there really a good example where the limit comparison breaks while the direct comparison test works?
Yes. And actually, so I'm going to tell you guys this again at the end of class. But when I was going through these notes and whatnot and trying to decide what I wanted to cover, I found that I had many more problems that I was interested in sharing with you, right? And so I have this written down at the end of this. It's actually in the next week's notes. It's comparison test bonus problems. I'm going to record me doing these bonus problems here, and I will post it, in all of the normal places. I can't give you attendance credit or anything like that for watching these. But I also wanted to invite you. I'm going to record this tomorrow, Saturday at 5 p.m. So if you want to come and hear the live version of this and ask questions and all that sort of stuff, you're welcome to join, even though I'm, just springing this on you now, and you're certainly not obligated to by any means. But if you guys would like to come and hear more problems being done about the comparison test, these are more difficult ones. And in particular, this one right here answers the student's question. This one right here turns out any reasonable limit comparison test that you attempt with this doesn't work out so well. And yet we can solve this with a direct comparison test fairly easily. And so this right here would be my answer to the student's question. So again, I'll remind you guys maybe at the end of class, or I'll try to remember to remind you at the end of class, that if you want to see more comparison theorem problems, I'm going to do them. But we have to move on. Monday, we have to talk about the alternating series test 11.5. We don't get any more class days dedicated towards the comparison test, but I have more problems that I want to do, so I'm going to do them. You guys can watch it or not. Okay. So let's do a problem here. I'd like to use the direct comparison test to determine if this right here converges or diverges. And so the big thing with any of these comparison tests, you have to decide what you're trying to compare with. And this came up a lot in chapter 7 as well. And so I think the most natural thing to compare this with is going to be 1 over n to the 5th, right? So I'm going to say this, and for the time being, I'm going to say versus this right here. This is a very natural thing to compare with, because we can quickly say that summing up 1 over n to the 5th from n equals 1 and beyond, we know exactly what's going to happen to this thing. Remind me, guys, from last time, is this going to converge or diverge? So far, all good answers. Yes, thank you very much. So this converges by the p-series. And so maybe there's lots of other things that you could compare with, right? But nothing's going to be as simple as this that you can just look at it and say, I know right away this converges because of p-series, right? And so when you check and you say, well, okay, if I'm considering the direct comparison test, I have to know if this is bigger or smaller than the thing that I started with, right? And so we have to spend a little bit of time. And remember when we were talking about, even though I didn't give any formal class time to it, unfortunately, right, that when you divide by more, you get a smaller result. So the fact that I have this +2 right here, I'm dividing by more. And so I get a smaller result. And so that's why this should really be less than or equals 2. Okay, so if you have then a bigger series, right? 1 over n to the 5th is bigger for each one of the terms. And you sum this up and it goes to a finite number. It converges. Is there any way that a smaller thing, in particular this one right here that we were tasked with solving, is there any way that this then would go to infinity? No, right? If something larger, when you add up all of the terms, doesn't go to infinity, it goes to something, I don't know, whatever, we'll say 3. It's probably something horrible like pi squared over 6. Actually, I know this doesn't have a nice expression or anything like this. They just call it zeta of 5. You can see where the 5 comes from at least. And this has to do with the Riemann zeta function, but okay, zeta of 5. But yeah, this is going to go to something less than that, right? So this also converges by the direct comparison test. All right, one more example, and then example 18 here, and then I promise to call on some of these raised hands and whatnot. So this is how you could solve this problem using the direct comparison test. I'd like to show you the same sort of thing for the limit comparison test and what my general thought process is. For the limit comparison test, again, we're going to be making the same comparison here. But when I'm thinking about limit comparison tests, and a good way to think about these in general to solve more complicated ones, is that I'm going to go through each factor and I'm going to take the most important piece. So that is, when I'm looking at 1 over 2 plus n to the 5th, there's really 2 factors. There's 2 pieces here that I need to be concerned about. There's the numerator, and then there's the denominator, right? There's only really those 2 pieces being multiplied together or anything like that. So in the numerator, the most important thing in the numerator, well, there's only one thing here, right? It's 1. So I have to leave that. And then in the denominator, again, I want to choose the most important thing. So in the denominator, we have a 2 and we have an n to the 5th. And so I have to tell you, what do I mean by important, right? Remember, n goes off to infinity, right? So imagine as you plug in, n equals 10, n equals 100, n equals 1,000. When I say important, I mean the most substantial or the most significant, right? When you plug in very, very large numbers, who cares about that 2, right? You think that whatever Bill Gates cares about $2, right? So when you have very, very large numbers, +2 doesn't really matter a whole lot, right? It's not as important. So the most important thing here from the second factor, the piece that's in the denominator here, is n to the 5th. This is going to yield very, very large results, while the 2 just is always 2. And so my claim is, with this line of thought or this line of reasoning, that we can come up with a good comparison, that this is a good comparison. But we need to verify that this is a good comparison. And the way that you do that using the limit comparison test is that you take these as a ratio of one another, and you compute this limit as n goes off to infinity. So you have your a sub n's and your b sub n's. It doesn't really matter which one you choose for your a sub n's and which ones you choose for your b sub n's, by the way. So I'm going to choose my a sub n's going to be my simpler one. And my b sub n's is going to be my more complicated one here. And okay, we have a lot of fractions over fractions. I'm interested in evaluating out this limit here. And when we have fractions over fractions, remember, we can always choose to multiply by the reciprocal. So I'm going to have my one fraction that's already in the numerator here. And instead of dividing by that other fraction, I'm going to multiply by the reciprocal. So I'm going to go ahead and multiply it by 2 plus n to the 5th divided by 1. That's the reciprocal of 1 over 2 to the n, 2 plus n to the 5th. And now you can see, almost even by looking at it, and especially if you're very strong with the maybe algebraic way of solving these, that you can probably just look at this and say, the limit's going to be equal to 1. Now, we could also see that if you want to do this using the Calc 2 method, right, that let's go ahead and combine. It only takes maybe one more line or so. We have 2 plus n to the 5th divided by n to the 5th. This is going to be an infinity over infinity sort of situation. We can use L'Hopital's rule with this. And when you use L'Hopital's rule, you get the limit as n goes off to infinity of 5n to the 4th, right? That the derivative of 2 is just 0. And in the denominator, we also have 5n to the 4th. So now these perfectly cancel out. And here you would see that the limit is equal to 1. Again, we have to remember, what does it take in order to actually tie these things fates together according to the limit comparison test? And the big thing that we need is that we have any positive constant here. What we're looking for is a real number that's bigger than 0. If this was equal to 0, then we haven't made a good comparison. And if it's equal to infinity, we haven't made a good comparison. But if you get any other result out, any other constant c that's bigger than 0 and not infinity, right? It's a finite number, then we've made a good comparison. And we can say that whatever fate one has, so too does the other, right? And in particular, we can say, highlighter, since 1 over n to the 5th converges by p series, we know that our more complicated one, 1 over 2 plus n to the 5th, also converges by the limit comparison test. And this is typically the work that we expected of students, when we had the handwritten exams and all that sort of stuff. Still, in order to maximize your partial credit, this is exactly what you should write. To make sure that you're getting a good amounts of partial credit for this sort of stuff. So we showed that they tied their fates together. We said that, well, we can quite quickly determine that this one converges, again, because of p series. And so we know something about our more complicated one. Okay, so with that, let's go ahead and take a few questions. Anito, I'll give you the floor first.
Oh, yeah. So you know how in chapter 7 we had like the many different ways to solve integrals, and then in this chapter we have like the many different ways to see if a
Yes.
series converges or diverges and whatnot.
Yes.
And so we have like a chapter in which we had like 7.5, I think it was, in which it was like how to determine which kind of thing to use.
My dream is that we'll be able to sneak that into like an exam review day. There is one in the textbook 11.7, I believe. I don't remember the exact name for it. So there is one written in the textbook, but this may have been one of the things that end up getting chopped because of the missing week that we had, right?
All right.
So maybe that'll be something that we can fit into an exam review day. Maybe that's another Saturday video or something like this. But yeah, so yes, it exists in the textbook. No, we don't have time dedicated to it in our schedule, unfortunately.
All right, for sure. And one quick question, when doing the limit or like comparison tests in general, does it matter like when it starts, like from n equals 1 or n equals 2 or whatever to infinity?
Nope. Again,
right.
So long as you don't do something silly.
Of course.
No, it doesn't matter.
Naturally. Thank you.
Yep, of course. All right. Any questions in the Q&A, Yuan, that we should talk about?
One is asking, I think it's example 11, what if is not greater than rather than less than?
Yeah. So that's a good question. And that's exactly what I'm doing next. So with example 19, I hope to tackle this exact issue. So at the beginning of all this, I told you guys that I believe that the limit comparison test is stronger than the direct comparison test, and that it can easily solve about like 90, maybe 95% of the problems that you're likely to see in our class. Not that you can, all the way eliminate the direct comparison test. And there are examples, as I alluded to, of situations where you do need it. But I'd like to show you a simple problem, this one right here, simple, that the direct comparison test has a hard time with. And we'll see the limit comparison test doesn't have a hard time at all. So again, same sort of situation. I'd like to try the direct comparison test here. Then I'm going to do the limit comparison test, same exact thing. And so let's see what happens. Here's one. Again, we have 1 over 2 plus n. We're interested in figuring out if this converges or diverges. And of course, the natural thing to compare it with is 1 over n. Because we can say very quickly, right, by looking at this thing, that if we were to sum up this 1 over n business, that this diverges. And again, by p series. Or we even gave an exact proof of this in class. This is the harmonic series, right? So we know that this one diverges. Now, just like before, right, I started off by saying this versus, right? This is the natural thing probably to compare with, because it's so easy to just look at it and say whether it converges or diverges. However, when you go ahead and you set up this inequality, just like last time, when you divide by more, aka that addition of 2, right, you get out a smaller result. Think about 1/3 versus 1/5. So 1/3 versus 1/5, right? Obviously 1/5 is going to be smaller. So adding that 2 into the denominator has yielded a smaller overall result. And so you have this larger thing going to infinity. Does that mean that a smaller thing must also go to infinity, that it must also diverge? And sadly, the answer is no. A smaller thing, maybe it still goes to infinity, but maybe it also goes to something like 13, right? Maybe it actually converges. Maybe it's so small enough, right, that it actually converges. So unfortunately, the direct comparison test fails with this comparison. Sad face. Now, if we have time, we'll talk about what the correct comparison should be if you wanted to, if you were very stubborn and you wanted to really, really use the direct comparison test. There is a way to do this, but it requires another level of cleverness, right? And yet, when we use the limit comparison test, this is very straightforward. Again, kind of if we use that same strategy, where if I look at the numerator and the denominator, and I go across all of my factors here, right? In the numerator, there's just a 1, and in the denominator, again, 2 versus n. N's going off to a million, a billion, a trillion, right? It's going off to infinity, right? That's going to be so much more significant than 2 is. And so I'm going to go ahead and compare this with 1 over n. Now, as before, we already said that 1 over n is going to diverge if we sum up all these things, right? If we were considering the series. But I would like to show you that these are two comparable sequences, right? Two comparable series. So we are going to go ahead and take the ratios of these things. So I'm going to go ahead and do my 1 over n here, and divided by 1 over 2 plus n here. My a sub n's divided by b sub n's. Let's take one line to simplify just algebraically. So instead of dividing by a fraction, I'm going to go ahead and multiply by the reciprocal. By the way, you'll eventually be doing so many of these that you probably won't even write this first bit here, that you'll just go right to the next one where you already are multiplying by the reciprocal. And now, again, if you're very strong with the algebraic side of things, you look at this and you say, well, these are polynomials of the same degree. You look at their ratios of the leading coefficients, so you get 1 over 1, or this just goes to 1. Or if you'd like, you can use L'Hopital's rule. And when you take the derivative of the top, you get 1. And when you take the derivative of the bottom, you get 1. And now you can see there's really nothing to plug in for n as it goes to infinity. So you get 1. Again, we don't care that this is 1. 1's a fine number and everything. What you're looking for is any positive constant. Any positive constant, finite, right? So you don't want it to be infinity. So long as it's not 0, so long as it's not infinity, you've made a good comparison. And these two will share the same fate. According to the limit comparison test, there is no question now, right? What one does, so does the other. So we say, since 1 over n diverges by p series, so does 1 over 2 plus n by the limit comparison test. The limit comparison test has solved this, while the direct comparison test failed. That's why I say that the limit comparison test is stronger. And it's nice because you don't have to worry about all of these inequalities and which one's bigger or smaller and all that sort of stuff. So I think that this is more straightforward too. And I like the limit comparison test whenever possible. So, okay. that's showing, maybe I should highlight some of these answers, by the way. I should really, so does, maybe I'll just write down here just to get it right next to it, right? It diverges. This thing diverges by the limit comparison test. That's the answer, right? All right. Let's go ahead and take a few questions. Michael, I don't think we've heard from you today. What's your question?
Hey, I'm confused. When the I know that the thing converges, but when it converged to 2,
One more time.
when the limit comparison theorem of 1 over 2 plus n converged to 2?
So you have to be careful here. First of all, when you say, something converges, it's not the series, right? We said that the series diverges. So you can talk about this limit right here, right? And this limit, you could say that it converges. But notice that when you take the derivative here, right? The derivative of the top, well, the derivative of 2 is 0 and the derivative of n is 1. And when you take the derivative of the bottom, you get 1 over 1. So this actually gets closer and closer to 1.
Oh.
So again, you can kind of see how insignificant that 2 was. That could have been a 2, that could have been a 5, that could have been 100. That doesn't matter, right? What really matters is the n portion. That's the more significant portion here.
Yeah, that was my mistake.
Okay. Yeah, no problem. Super. Let's take one more here. Matthew, I don't think we've heard from you.
Hi. I'm just still, why is this one any different than 17? Is it because it converges? Or, like, I'm confused on why the divergent test or the direct comparison test didn't work on this one compared to number 17.
Yeah, so my hope with showcasing these two is that sometimes the direct comparison test works perfectly fine, but sometimes, the smallest change throws it off, right? And in particular, if I wanted to create a problem that the direct comparison test couldn't solve with this one right here, all I would have to do is write 1 divided by n to the 5th minus 2. Because again, the natural thing that you would compare with is going to be 1 over n to the 5th here. And yet now, notice that 1 over n to the 5th, right? You're dividing by more. You don't have that minus 2. So when you divide by more, of course, you get a smaller result. And so since this thing converges to some, right? And again, I'm being a little bit improper here. I'm cutting some corners here because when I say it converges, I mean the series converges. So when I sum up all of these, they converge. Does that tell you anything about a bigger series? Well, no, it could still go off to infinity. And so you can see that these things are very fragile. That's what I wanted to showcase here, is that just the slightest things, right? The inequalities don't work out as you would hope. And so overall, I would like to emphasize that when possible, use the limit comparison test.
Okay. All right. That makes sense.
Cool.
Thank you.
Yeah, no problem. By the way, so I want to do another problem here, but I told you, right, especially with the phrasing here, use the direct comparison test. If you did want to use the direct comparison test, you can do this, but the comparison that you would have to make, like I said, you have to be more clever with it. And so since what, I wanted a 2 here, that's my bad. So we'll say since n is greater than or equal to 1, right? Notice that our starting point here is 1 and it goes larger than that. Then if you were to graph these two, n plus 2 and 3n, you'll see that 3n is always larger than n plus 2, except for at n equals 1, they're actually equal, right? But you can imagine, right, with a bigger slope and everything, basically the picture looks like this. You have 3n like this, and then you have n plus 2 that looks like this, kind of a lesser slope. And so they cross here right at 3 when n is equal to 1. But in general, the thing with the bigger slope ends up being bigger. And so with this, you could say that 1 over 2 plus n is actually going to be larger than or equal to, right? If I divide by more, in this case, the more is the 3n, we get out a smaller result. And so now, because this one is a smaller result, and still we can factor out that 1/3, and we can say that the series diverges quite comfortably, we'll know that the larger thing must also diverge. It must also go to infinity. And so you can see here that this requires another level of cleverness, right? It is possible, but it requires a clever argument. Why did I choose 3n, right? That's maybe still not exactly clear. And so that's why, again, I want to emphasize, whenever possible, please use the limit comparison test. It's just so much cleaner. All right, let me show you a more complicated example here, and then I'm sure there, oh, wait, let's take at least one question from the Q&A here. I don't want to ignore the Q&A. Yuan.
Okay, let me pick one. This one I was answering now is, for example, 20, if the limit is 1, how does that, so the constant usually people is confusing. The students are very confusing. It's at 0, infinity, and it's a constant, or it's necessary to be 1, or any other constant could work too.
Yeah, that's a great question. I mean, this constant here, it could have been 5. It could have been 100,000 for all I care. You know, any positive constant will show that these are good comparable series, that what one does, so too must the other, right? And so any positive constant as a result of the limit would be, I would be perfectly happy with that. That ties their fates together. So again, kind of, this all comes back to our statement of the limit comparison test. What we're looking for in order to show that the series are comparable is that when you take the limit of the ratio of the terms, you get a finite number that's not 0. Right? Of course, everything's positive here, so you're not worried about getting negatives, right? So long as you get a finite number that's not 0, then you're happy. Actually, this is probably worthwhile here, that why don't we try to do something wrong really quick? Suppose I said that this right here was comparable with 1/n². Let's say I chose a bad comparison function. What then happens, right? So I choose this and I say, okay, well, this one converges, right? Because P series. So when I sum them all up, it converges. And so therefore, I'd like to conclude that this one must also converge. By the way, we know that's wrong. We know that this diverges, and we've already proven it. But let's showcase why you can't really tie their fates together. When you go and you do the limit as n goes to infinity of my a sub n's divided by my b sub n's. And again, we're going to go ahead and do some algebra here. And instead of dividing by a fraction, I'm going to go ahead and multiply by the reciprocal. So 2 plus n up here divided by 1. And now we do have an infinity over infinity situation. So I'm going to go ahead and use L'Hopital's rule. So when I use L'Hopital's rule, I get, well, what, 1 on the top and 2n on the bottom. So now as n goes off to infinity, this is equal to 0. And so you can see that I've chosen a bad comparison, that these are really not comparable series. What one does, the other doesn't care about whatsoever, right? And so you need to make a good comparison, right? 1/n is a good comparison. And the way that we showcase that it's a good comparison is that we take this limit. And again, we're looking for some number, not 0, and it should be not infinite either. Excellent. Okay. Well, last time we didn't really get to this one. I posted the solutions for this in the 11.3 notes. But you can see that this one right here has something to do, I hope, with inverse secant. Hope you guys still recall from chapter 6, whatnot. Back then we were using x as a variable. So we would say that this right here, if you were to integrate it, that you would get inverse secant. And, you know, since I do have my full set of notes at my disposal, let me just zoom up here. And here's all the work that went into this. We had to say that it was positive, that it was continuous, that it was decreasing, right? All of these things take time, a lot of hypotheses. Once we integrate this, right, we have to think about inverse secant and what this is approaching, right? And we found out that the improper integral here turns out that it gets very close to pi over 6. right? But again, you have to remember, what does inverse secant look like, and what do the asymptotes approach, and all that sort of stuff. And we said, well, since the improper integral converges, we know by the integral test that the series must also converge. And so this is quite complicated, right? And I gave an entire page to do this, and we didn't even get to it, but it took a lot of time to write it out. And so I'd like to showcase here that the limit comparison test will solve this much easier for us. It's a lot more reasonable. And so, okay, we'd like to determine if this converges or diverges, starting at 2 and going beyond. And so again, what we need to start off with anytime we want to use the limit comparison test, and I see no reason not to use the limit comparison test. Like I said, this works 95% of the time. We need to figure out what to compare with. What is a good comparable series? And so again, we're going to go along all of the factors. And so looking at in the numerator, we have only one thing, 1. And so it's the most important piece. Now in the denominator, we actually have 2 factors. There are 2 things that are being multiplied together. And so when I say factors, right, that has a very specific mathematical meaning, right? All of the things that are being multiplied together here. And so we have the 2 factors are, we have the n piece and we have this square root piece. And so you do need to consider those as different factors. And so when I look at the n piece, well, there's only one thing there, right? It's n. However, when I look at the square root of n squared minus 1, right? I have to think, what is more significant as n goes off to infinity? The n squared or the minus 1? Well, the n squared is going to really contribute to this, right? Because again, eventually you're plugging in n equals 1,000,000 or 1,000,000,000, right? Very, very large numbers. And so the fact that you're subtracting away 1 doesn't super matter here. And so I'm going to go ahead and choose the n squared. Now notice that I can't just get rid of the square root here. I have to leave that. Let's take a line or so to simplify this, right? So if I take something and I square it and then I take the square root of it, and it's a nice positive number, right? These things perfectly cancel and we just get another n. And so this right here is the same thing as 1 over n squared. So this right here is my simple thing that I should compare with. And of course, we can look at this and say by p series that it converges, right? So I'll just write that down right here, right? So 1 over n squared converges by p series. Oops. It's a bad way to spell series. There we go. All right. I've taught you the technique to show that, I think that this is a good comparison to make, but let's verify, right? And again, whenever you want to verify, you take the limit as n goes to infinity of the ratio of these things. So I'm going to go ahead and take my simpler one. Now, by the way, this is kind of maybe not be obvious at this point, but my claim is that when you go and you do this limit work right here, it's better to take the more complicated one. I'm going to use this. So instead of looking at the 1 over n squared, which is really, when I go and I look at my result, I can quickly say, looking at that it converges by the p series. Remember, that's equal to this more complicated thing. And so I'm going to use this more complicated thing, and hopefully you'll see why. And if you don't, I recommend that you try using this other thing, the simplified version, and seeing that maybe it's not as obvious what steps you need to take. So I'm going to go ahead and use this one. And then, of course, my b sub n's are going to be my original thing here. So a sub n's divided by my b sub n's. Again, as always, let's go ahead and take one line to clean things up. So 1 divided by n times root n squared. And instead of dividing by a fraction, we're going to multiply by a reciprocal. Notice that one of these n's is going to just outright cancel here. So that's very nice. And what we're going to be having left over is the square root of n squared minus 1 divided by root n squared, which, by the way, if you didn't have this here, right, it would just, if you use this piece instead, it would just have an n in the bottom. But notice when both of these have the square roots in them, it's very suggestive, and remember when we applied L'Hopital's rule earlier in chapter 6, right, these square roots have sometimes this habit of dancing across the division, right? And kind of you apply L'Hopital's rule infinitely many times and it doesn't help you at all. but with the two square roots written there, one idea that we found to be quite useful is to combine them into one big square root. And that is the correct way to go here. And that's why I think writing it in terms of the slightly more complicated version up here, right, actually has good value to it. Okay, so now with this, remember you're allowed to push the limit just inside of the square root. So I'm going to push the limit inside of the square root because the square root is a continuous function. And so now my goal has become, can I figure out this limit here? And okay, maybe we've done so many of these that you'll just quickly say, that's 1, right? Again, the numerator and the denominator have the same degree. They're both squared. And so you take the ratio of the leading coefficients, 1 divided by 1, you get 1. Don't forget, by the way, that this is inside of a square root, even though the square root of 1 is 1. If you were to get any other result, for instance, 4, right? The answer would not be 4. And WebWork checks these things, by the way, right? It had lots of boxes. The answer is not 4. The answer is 2, right? Because the square root of 4 is 2. And so, yep, do be careful with that. This right here has shown that we've made a good comparison. Sometimes students, they just say a 1 here, right? And they say, it converges, right? Well, no, right? The 1 there doesn't tell you if it converges or not, right? The 1 tells you, did you make a good comparison? Notice that here's one that the answer was that it diverges, but we were able to confidently say that because we made a good comparison and we got out this, the limit here was a nice positive constant, not infinity, not 0. And so the same thing here, that 1 there does not tell you that the series converges. The 1 there tells you that you've made a good comparison. And so now you need to go back up and compare, right? Take the thing that you want to know something about, the series over here, and we are able to make a good comparison with 1 over n squared. And again, this series converges by p series. So by the limit comparison test, our more complicated one, 1 over n root n squared minus 1, converges. So this is the right answer here, but it has everything to do with the fact that comparing with our simpler series. That 1 right there doesn't actually tell you if it converges or diverges, just if you made a good comparison. All right. So I hope that at very least you see that you didn't have to, it's not maybe as long, and you didn't have to do any of that stuff with knowing about secant inverse and all of this sort of stuff and how the asymptotes there work. So yeah, at very least we got to skip all of that stuff. And so I hope and you didn't have to worry about the positive continuous decreasing, right? The limit comparison test has relatively few hypotheses. And so that's why, again, I like this one the best. All right. So with that, I see it's after 2:40. So this is where, of course, we'll end. We'll stick around for a few minutes and take some questions. Again, I have office hours today from 4 until 5. So if you have some time, if you want to do more math, come and hang out then. And then finally, there's another 4 pages of comparison theorem problems that I knew that I had no hope of ever being able to cover, but I thought it would be very useful. Has some more good examples. I will record that over the weekend and post it on YouTube and D2L and all these sorts of things. Again, you don't get attendance credit for watching that, but I do think it will help, as you prepare for quizzes, exams, all that sort of stuff. And if you would like to come and ask questions and be in the live version of this, I'm going to be recording it tomorrow at 5 o'clock. So Saturday at 5 p.m. If you're available, if you're bored and you don't have anything better to do on a Saturday evening than math, come and hang out with me. So same Zoom room. Yes, that's a good point. Same link as the lecture. That's where we're going to be. Yep. Good question. All right. With that, I'm going to stop the recording.